Nope. How do you wear this? No, this is mine. So is this the front or is this the front?
So it's like this. The cable
Oh,
comes
okay.
from back.
Okay.
Yeah.
All right. So this is okay. Maybe I look like an alien now.
Can someone check if the live stream is okay? On YouTube? Yeah? Okay, I'll just assume that it's okay because I see some stuff over there. So I guess we can start. So it's my pleasure to introduce Gururaj Saileshwar today in today's SAFARI Live seminar. So Gururaj is an assistant professor in University of Toronto, and he did lots of works in computer architecture and security, hardware security. And he's particularly interested in microarchitecture security, memory security, in particular Rowhammer, and also security for machine learning systems. It's quite exciting to have him here today. Before going to the talk, I want to mention a few of his awards. Like his PhD dissertation is recognized as the best PhD dissertation by the host community. And then he also got a couple of honorable mentions from SIGARC and SIGMicro, which are the dissertation competitions as part of ISCA and Micro, which are the top venues in computer architecture. And he had several like top picks and best paper awards, so it's quite impressive. So today the talk is about robust mitigating Spectre and Rowhammer in future systems. And without further ado, please go ahead. Welcome.
Thanks, Gary. Can everyone hear me? Is the mic working? Perfect. All right. So today I'm going to try to convince you that if we really want to robustly mitigate Spectre and Rowhammer, we don't necessarily need good defenses, but we really need good offenses as well, right? So today, the holy grail of microarchitectural security or general security is mitigating Spectre and Rowhammer in a robust manner. This is because regardless of the security solutions you have at the software layers, if you have these kinds of vulnerabilities at the hardware layers, the security of the entire system breaks down. One major challenge, actually, there are two major challenges in microarchitectural security today. The first challenge is that for attackers, it's really difficult to estimate how large the threat landscape is because hardware is a complex black box. So you really don't know when you're done, right? Where the new attack is going to come from. At the same time, for defense, it's really hard to build robust and practical defenses because as computer architects, we always face this security versus performance trade-off. We want practical defenses that are going to incur the minimum performance overheads. And companies like Intel and AMD often end up making this trade-off about security versus performance. As a result, what happens is that defenses break under certain corner cases with new attacks. And then new defenses get created to defend against these existing attacks. And then they again get broken by newer attacks. So this arms race continues between attack and defense in the space of microarchitectural security. So how can we end this arms race? That's really the holy grail. In this talk, I'm going to try and convince you that the only way to get ahead of this arms race is to come up with good offensive tools that we can apply at design time and thus be able to detect vulnerabilities at design time so that they can be fixed at design time, so that we don't put out insecure solutions. So I'll try to.
There's something over there blocking it.
Okay. Okay. So I'll give you one example of this kind of work as part of AMuLeT, which was published in ASPLOS earlier this year, where we came up with a tool to detect leakages at design time in microarchitectural defenses. I'll also give you some sense of this line of work through some of the recent works on Rowhammer defenses, where applying an offensive mindset has allowed us to come up with better defenses. So I'll talk about QPRAC, which was one of the works demonstrating new attacks and defenses in the space of PRAC that were published at HPCA this year, and then also give you a sense of how new kinds of vulnerabilities can exist due to these defenses by talking about a new work that's going to appear at ISCA in a couple of months. So without further ado, I'll jump into the first work, AMuLeT. So most of you would be familiar with transient execution attacks like Spectre. These attacks exploit prediction mechanisms to leak more information than what is accessible based on program semantics. Paul Kocher had this prophetic statement in 2019 that Spectre is a messy class of vulnerabilities, right? And that has really proven to be a prophecy that came true. Because of the large gamut of prediction mechanisms that exist in CPUs, we've had tons of new vulnerabilities discovered in the last several years. The architecture community has not sat idle. They have also come up with many, many new countermeasures all the way from 2018. And there are many paradigms of these countermeasures, including making speculative loads invisible, allowing speculative loads to perform certain state changes and then rolling them back when unsafety is detected, or tracking speculative changes while they are happening using something like taint tracking and blocking unsafe changes from being made. Unfortunately, all of these defenses have been broken by subsequent attacks that came out months or years after these defenses were proposed. And as we speak, new countermeasures are being created. So in Usenix security earlier last year, when we were doing this work, a new defense came out that also did some tracking in cache line fill buffers to buffer speculative operations. So should we wait many years to discover whether this defense is secure or not? The short answer is no. It's not acceptable to wait several years, because in several years, these defenses might get fabricated, commercialized, and it becomes very hard to detect and patch vulnerabilities after commercialization. So we really want to do this detection of vulnerabilities early on in the design phase. Before I tell you how to do that, let me first explain why these countermeasures keep getting broken. So the main reason is because currently we lack principled techniques to detect insecurity in these countermeasures at design time. There's no systematic method to do this. And as a result, the only way that we test the security is by having some grad students sit in a room, think deeply about a defense, and reason about why it's secure or not. And all we need is another grad student sitting in another room to figure out a corner case where this defense breaks down. And as a result, we continue to have this arms race, right? So because we don't have systematic ways of testing these defenses, corner cases remain in these defenses where the security breaks down. So the takeaway here is that we need defenses, we need techniques to test the security of these defenses at design time. So the state-of-the-art testing techniques for testing for vulnerabilities like Spectre typically apply to commercial CPUs. So one example of this is a tool called Revisor, created by Microsoft, which uses black box fuzzing to test target CPUs for leakages. The way they do this is by generating random test programs, running these programs against a leakage model that is implemented in an emulator that allows them to observe what's the expected leakage from these tests, and then running the same tests on a target CPU where they're able to compare the expected leakage on an emulator and the observed leakage on the target CPU, and they try to find test cases where the expected leakage is the same, but the actual observed leakage is different. And what this means now is that you found a new source of leakage that you did not expect, right? That's not captured in your leakage model. And this has been successful in finding vulnerabilities in real CPUs and so on. The problem is that these techniques currently are only applicable to commercial CPUs. And we really want to be able to not wait until these hardware designs get commercialized to actually start detecting these kinds of leakages. So this is not a problem that only Revisor suffers from. Many other testing techniques also are only applicable at the RTL stage, which is also often too late to detect some of these speculation-based vulnerabilities, because by the time you generated the RTL, it's already too late to change a microarchitectural feature like a predictor, because the modeling of these predictors really happens in simulators, which is much earlier than the RTL stage. So we want some techniques that are applicable early on in the design phase when these predictors are actually being formulated. On the other hand, there are formal methods-based tools that are applicable for modeling the security of these defenses at the early stage of the design, but they are not scalable. Often, some of these tools can only detect leakages in programs of around 10 cycles, and even that takes several hours. So for practical programs, these tools are even not applicable, and they require a lot of manual modeling effort. So we really seek automated testing tools that are applicable early on in the design phase, and that are very easy to integrate with new defenses and new hardware techniques with minimal developer effort. So that's the motivation for our work, AMuLeT. This was work done in collaboration across multiple universities and also with folks at Microsoft, and led by two of my students at U of T. The key idea of AMuLeT was to extend the testing mechanisms like Revisor and apply them to the early stage of design in microarchitectural simulators. This allows AMuLeT to detect speculative leakage in countermeasures that are implemented in these simulators. So our high-level testing methodology is we still create random test programs and define a leakage model for a particular countermeasure we want to test, and run these tests on the leakage model on an emulator and collect the expected leakage through a contract trace, and also run these same test cases on a simulator, which has the countermeasure implemented. And we extract microarchitectural traces from the simulator that an attacker might observe. And we test or compare the contract traces and the microarchitectural traces. We try to still find two test cases, which is an instance of one program and two inputs to this program that generate the same contract trace or the same expected leakage, while generating different hardware traces or different microarchitectural traces, or the observed leakages on the simulator. And if we can find such an example, then we found an unexpected leakage, right, in the countermeasure that we did not model in our leakage model. And then we can go and analyze this leakage instance and try to see why it's leaking. So, so far so good. What's the challenge? Well, porting some of these testing frameworks to simulators introduces several issues. The first problem is that simulators allow you access to the entire microarchitectural state of the CPU. This is often like drinking from a fire hose. You don't know what you're seeing, and you might actually end up detecting leakages that are in fact not even realistic for an attacker to pull off on a real system. Second, CPU simulators are actually slow. They are much, much, much slower, often tens of thousands of times slower than a real CPU. So how do we find vulnerabilities in these simulators in a reasonable amount of time? And finally, the search space for these vulnerabilities is actually huge, right? Like you're trying to find certain sequences of microarchitectural states within the microarchitectural state space, which is, can have trillions of states. So how do we find instances of leakages within this large search space in, again, a reasonable amount of time? Okay, so to go over some of these challenges one by one, first, we observe that we don't need to include the entire microarchitectural state because some of these states are actually very easy for the attacker to observe, while some of them are extremely hard or even impossible for the attacker to observe. So we want to restrict our microarchitectural trace to states that are realistic to an attacker to observe so that the leakages we end up detecting are realistic to exploit. We observe that simply exposing the cache and the TLB states is sufficient for detecting a large fraction of these leakages. And most defenses also protect against these states. So this is good enough for our testing. But we can easily incorporate other microarchitectural state like branch predictor state or even sequence of certain operations within the microarchitectural trace. And this provides us more leaks with some impact to testing time. Okay, so the second challenge of speed is a slightly harder challenge to address. When we hooked up our testing framework to the simulator and started testing, we observed that these tests were really slow. Often it would take almost a second to just test a single test case of about 50 instructions. And so when we dug deeper, we observed that the time to actually simulate these 50 instructions is a very small fraction of the overall testing time. Over 95% of the testing time was actually going in the simply waiting for the simulator to start up, which is actually pretty bad, right? Some of the simulators have gigabytes of state, and just starting them up, initializing all of these data structures takes a long time. So we came up with a better testing framework, testing harness, if you will, to avoid some of the startup costs. So rather than generating a test case and then running it on Gem 5 and waiting to get the results back and then running the next test case on a new version of Gem 5, we said, let's keep Gem 5 running, let's not quit it, and let's run a test harness that runs a loop of no-ops on Gem 5 on an almost infinite loop. And let's inject test cases directly into the simulated binary by overwriting the binary inside of Gem 5's memory. With this, what we were able to do is we pay the startup cost once, and then with each iteration of the loop, we can run a new test case without restarting the Gem 5 and avoiding all of the startup costs. With this, we were able to dramatically increase the speed of fuzzing. And now we are able to start running tests at almost 0.1 second per test. This gave us a speed up in testing of about 12x, but this also made testing more effective. Because now, if you notice, we are not clearing the microarchitectural state of the simulator after each test case. So the microarchitectural state of the first test case at the end of the test case becomes the initial state for the next test case. So we end up exploring more diverse microarchitectural states. And this increased diversity lets us explore more interesting corner cases in the design. And this leads us to discover more leakages per unit time. Finally, we want to amplify the chance of vulnerability being detected if it exists. And for this, we observe that if we one building block for of a vulnerability is it being able to leak information out through a covert channel, and a covert channel requires contention on a microarchitectural resource. So what we observed is that we can artificially increase the contention on microarchitectural structures by reducing the sizes of these structures. So what this means is by random testing, each test has a higher chance of activating a covert channel, and so we have a higher chance of observing a vulnerability if it should exist. With this, by decreasing the sizes of some of our structures like misstatus handling registers, we started to find vulnerabilities in designs in minutes where we couldn't even find it in almost an hour of testing. Okay, so we now have all of the building blocks of our tool, AMuLeT, and now we have the capability of running the first systematic test campaign on a variety of microarchitectural defenses. So we ran this campaign across 4 defenses in different versions of Gem 5. And these test campaigns took between a few tens of minutes to a day, based on how fast the defense itself could be simulated. And we did this across 4 popular defenses published between 2018 and 2024. And surprise, surprise, we found vulnerabilities in all of these defenses. AMuLeT actually was able to find 3 previously known and 6 unknown instances of leakages across the defenses, and often in seconds. And note that we also started to find leakages in the latest speculative countermeasure called SpecLFB. So I'll go over briefly the types of vulnerabilities we found with AMuLeT. The first class of vulnerabilities were simply protections that were unimplemented in the defense on certain paths of execution. Some of these we already knew, like for instance with InvisiSpec and STT, we knew that the certain aspects of the microarchitecture are not protected, and AMuLeT started finding these automatically. In one example of a defense called CleanupSpec, we found instances that were unknown previously, where certain protections were not implemented on, say, speculative stores or speculative stores that cross cache line boundaries. Next, we started finding implementation bugs in the defense itself. So for example, in InvisiSpec, we found a new bug where the protections were implemented correctly for L1 cache hits. They were also implemented correctly for L1 cache misses that don't evict any address from the cache. But if an L1 cache has a miss that ends up evicting an existing cache line, the protections there were not implemented properly. And this was simply due to a lack of understanding of how the protocol itself works. This could also occur in the production hardware. Third, we found instances of undocumented performance optimizations in a defense. In the case of SpecLFB, we found that the protections get removed if the speculative load is the first speculative load in a sequence of loads. We don't know why this particular optimization was implemented. This definitely improves performance by a few percentages, but this also causes leakages where it should not leak. And finally, we found some fundamental design issues in a couple of defenses where if there is interaction between speculative loads and non-speculative loads to the same address, this can lead to race conditions that again end up leaking information that was not expected by the designers of these defense. So overall, AMuLeT finds a lot of unexpected leakages, and it does so in seconds. So the takeaway from this work is that this is the first tool that can actually help designers of defenses test whether their defense actually holds up or not. And it can do so in seconds to minutes. And the hope is that with AMuLeT, we will enter an era where designers of these defenses can actually test whether their defense is secure or not, so that we don't end up with insecure countermeasures in the wild. I'll stop here and and check if there are any questions. Any questions? Yes.
structure sizes, right?
Yes.
So I was wondering if that could also lead to missing some intricate vulnerabilities completely, for instance.
Absolutely. That's a good question. So when we change the operating point, like the sizes of certain structures, we make vulnerabilities easier to discover, some vulnerabilities easier to discover, but it could mean that there are other vulnerabilities that are not discovered, but they would anyway be hard to discover if we were to test with the full size of the structures. So it's not like we are doing a great job by testing the default sizes of these structures. So I think there's more research to be done in this space to be able to find these hard to discover vulnerabilities. And yeah, so it's definitely a work in progress.
Thanks.
Any other questions? Yes. Yeah.
I'm just picking the microphone because of the YouTube.
Yes.
So you mentioned that you find out some implementation errors, mistakes, vulnerabilities.
Mm-hmm.
You also mentioned that when you have the security contract in like two different architectures, the same security contract, and they exhibit different vulnerabilities. So does it, in that case, like if we have an architecture that implements a certain security contract that doesn't exhibit any vulnerability to some sort of leakage, and the actual implementation exhibits that vulnerability, can we just say that that implementation is wrong? Like, isn't it the problem of the implementation itself rather than the architecture design, like the high-level idea itself?
So the contract basically models what we expect the design to leak, right? It's independent of the implementation, right? So think about it as the goals or the security properties of a particular design, right? So when we test a particular implementation against this contract, one implementation might be insecure, another might be secure, right? And the goal of this testing is to actually see if the implementation matches the contract that it promised, right? So you're absolutely right. A lot of these leakages that we discover may be implementation specific. So yeah, that's really the goal, right? To find implementations that are bad and to fix those implementations. Because at the end of the day, it's the implementation of a particular design that will be fabricated, right? Does that answer your question?
Sure, yeah, to some extent. So I'm a bit confused here because like compared to the previous work reviser, now you do the implementation on Gem 5.
Mm-hmm.
And of course, like since this is a paper, you do the implementation yourself as well, right? So it's not
No. So all of the defenses that we actually tested were using the open sourced implementation of the designers of these defenses. So
they were already like merged into the Gem 5
yes. So
repo.
on different, so they're not merged onto the main line of Gem 5, but think of it like we took the code of a particular defense implemented in Gem 5 already, and just first ran our tool on that particular implementation. So it's not like we introduced the vulnerabilities and detected them. It's simply detecting vulnerabilities that were introduced by other developers.
Yeah, of course. Yeah, that makes sense. Thanks for the clarification. My other question is more like a theoretical level, actually. I mean, of course, these fuzzers and random binary generation are quite practical tools in discovering a lot of leakage vulnerabilities. But when it comes to ensuring security, it's really hard to find a corner case. explore all the corner cases exhaustively by doing this random binary generation, right? So do you have some, I don't know, future steps in your mind to cover those cases as well?
Yeah, that's a great question. So I think fuzzing is not a replacement for more principled methods like, say, formal verification. They are really complementary. Fuzzing can only detect or demonstrate insecurity. It can't prove that a defense is secure or, yeah. So you might say, let's fuzz it, and you might not find anything. That doesn't mean that the defense is secure. So at the end of the day, you do need other orthogonal techniques to validate or prove that a particular design or implementation is secure. But they're really, but formal verification often is a hard problem, right? It requires a lot of manual modeling. It's often slow. So the goal here is to, while we work on all of those principled approaches, here's a quick and dirty way of checking if a particular defense implementation is secure or not, right? And fuzzing in the software world is now pretty much widely adopted by all big companies like Google, Microsoft. A lot of the bugs that they discover and fix today are discovered by fuzzing. So why not do it for hardware? Clearly, we have bugs in hardware. Why don't we do a better job of discovering them before they are, commercialized?
Yeah, sure. That's great.
That's really
Thank
the
you.
approach.
So,
yes.
Okay.
I have a follow-up question for Guraj's first question about the implementation bugs. I was wondering, what is the benefit of doing this with a Gen 5 based or like simulation-based tool? Because when we consider RTL, it's much closer to the final product, right? Like the implementation would be more accurate because you would have something closer to the hardware design. What is the benefits?
Yeah, that's a good question. So I think the key benefit of doing it in a simulator is that often new microarchitectural features are first modeled in simulators before you generate the RTL. So if you have a reasonable model of your CPU, which is what a lot of companies like Intel and AMD already have, they have reasonable models of the CPUs in simulators, you can actually check if this new feature breaks an existing defense, or if a new defense is being formulated, is this truly, is this insecure in ways that I didn't think of, right? This is not testing in simulators is not enough. As I said, once the RTL is generated, you have a more detailed description of your CPU. So we really should test at every layer of abstraction. You should test in simulators, you should test in RTL, you should also test after commercialization. We really need testing at all layers.
Okay, so the goal is not to replace it, I
Yes.
guess. Yeah, I think that makes
the goal
sense.
is to be able to discover these issues as early as possible.
Yeah, and then it can also help design
Yes.
better, I guess.
Yeah.
Okay, thanks.
Are there other questions for AMuLeT? So we actually on Zoom have several people from different time zones attending today, so it's impressive as well. I'd like to encourage them to speak up as well if they have questions. Otherwise, we can just move on with the presentation.
Okay. So if there are no further questions, I'm happy to continue this journey of offense and defense further. Moving on. So first part, we talked about Spectre. Let's now move our focus to Rowhammer. So the problem of Rowhammer is probably familiar to a lot of you, most of you. Basically, hammering one DRAM row repeatedly, rapidly, ends up causing bit flips in neighboring rows due to charge leakage from neighboring rows. And this is a problem because now an unprivileged software has this primitive of introducing bit flips or data tampering in data it doesn't even have access to. The main problem here is that the number of activations required to introduce a bit flip have been decreasing progressively, as technology has been progressing, and we're moving to smaller and smaller technology nodes. So it's the number of activations required to introduce a bit flip, called the Rowhammer threshold, has dropped by more than 10x in the last decade. So we really need solutions that are scalable to lower Rowhammer threshold so that we can have defenses that work in future DRAM. So in 2024, JEDEC, which is the DRAM standards body, came up with the biggest change that they have proposed in the last several years in regard to Rowhammer mitigation. They proposed this technique called per row activation counting, which was designed as a principal technique to mitigate Rowhammer. The idea is to have counters per DRAM row, and this will count the number of activations per DRAM row. And then when a particular DRAM row crosses a certain activation count threshold, called the back-off threshold, the DRAM is now going to signal an alert to the CPU. And this allows the CPU to send mitigation in the form of a command called RFM to the DRAM. And the DRAM now has time to issue mitigations to the neighboring rows of the row that received a lot of activations. This is good. This now allows the DRAM exactly to know which row is being attacked and gives it the time to mitigate the neighboring rows of exactly that row. So the mitigations are precise. But there's also some problems. To explain the problems, I'll first explain how the protocol for performing these mitigations. So whenever the activation that causes a counter to surpass a particular threshold occurs, an alert is raised. The DRAM sends an alert to the memory controller. The memory controller has some time to respond to this. This time is called the TABO act, or 180 nanoseconds, after which it sends the mitigation to the DRAM. So this time gap between the attack potentially being detected by the DRAM and the mitigation arriving from the CPU allows the CPU to perform some additional activations that can actually be weaponized by the attacker. This gap permits up to 3 activations, and this is actually a problem. Now it becomes super critical how you're tracking pending mitigations, because otherwise, if you don't track these pending mitigations properly, an attacker can actually use these additional activations between an alert and the mitigation to perform worse Rowhammer attacks. We'll discuss why this is a problem shortly. But the takeaway here is that you really need to track pending mitigations carefully. The problem is that PRAC, as a specification, does not specify how these mitigations need to be tracked. It just says you need a mitigation queue. Now, some of the folks from ETH came up with the first PRAC mitigation called understanding PRAC, or as we call UPRAC. This assumes that the DRAM implicitly can identify the highest activated row whenever a mitigation arrives. Unfortunately, if you're not tracking rows that require mitigation actively, you can have multiple rows that require mitigation at the same time. So identifying the most critical row that needs to be mitigated, the highest activated row, implicitly can mean that you need to search through all possible counters in the DRAM, which is actually impractical. So you really need a way to track rows that require mitigation in some sort of a queue to be practical. So a prior work called Panopticon from Microsoft did indeed propose a mitigation queue. They proposed a FIFO mitigation queue. So the idea here is that you have a queue where rows that are activated heavily get enqueued into this queue. So in this case, row A crossed a particular mitigation threshold, and it ended up in this mitigation queue. Row B crossed the threshold, and it's sent into this queue, and so on. Whenever the queue becomes full, the DRAM raises an alert to the CPU, and the CPU now has a certain time before it sends a mitigation. And the FIFO queue removes rows that require mitigation one by one. So first row A will be removed, then row B will be removed, and then row C will be removed, and so on. The problem is that this gap between alert being raised and the mitigation being sent allows the attacker extra opportunity to do malicious activity. I'll explain how this works. So we came up with a new attack called fill and escape attack against Panopticon that exploits these extra activations possible between alert and mitigation. So the idea is following. So in addition to, let's say the capacity of this queue is 3, our attack uses up more than 3 rows in being activated continuously. So in this case, we have 3 dummy rows, A, B, C, and 1 row T, which is our target row. And all of these are being activated at the same rate. And then we fill up the queue with the first 3 dummy rows. And so now the DRAM raises an alert to the CPU. And in this period where the queue is full and the attacker can do additional activations, the attacker now focuses on this target row and pushes this target row beyond this back-off threshold. Now you have row T that requires mitigation, but there's no space in the queue to insert this row for a mitigation. What happens is that the mitigation just simply loses the state that row T requires a mitigation. When a mitigation comes in, row A gets mitigated, which is a dummy row. Row T never gets mitigated. Next, the attacker again targets the dummy row, fills up the queue, and when the queue is full, only then it hammers the target row. With this, you can increase the activation count on the target row without it ever getting inserted into the mitigation queue. Because each time the row is identified as a potentially malicious target, the queue is always full, so we are never able to, the mitigation is never able to track the heavily hammered row as requiring mitigation. With this, by hammering row T only when the queue is full, we observe that the attacker can take the activation count of this particular row far beyond the back-off threshold, often to thousands of activations within a refresh window. With this, an attacker can surpass the protections of Panopticon and still continue to perform a successful Rowhammer attack simply by using these additional by using these additional ABO acts to perform the hammering. So we observed that the queue design is super critical for dictating the security guarantees of the implementation. And therefore, we came up with a new approach that tracks pending mitigations by not only using a FIFO queue, but by using a priority queue. The key design, or the key insight of our design is to actually use a priority queue that not only tracks the addresses that require mitigation, but also tracks their activation counts, the current activation counts. And this queue is ordered based on the current activation counts of these entries in this queue. So the priority is basically the activation count. With this, what we are able to do is whenever a activation occurs for a particular row, it's sent into this queue. So our queue is always full. And then what we do is even when the queue is full, if a particular row is receiving extra activations, it has the opportunity to be inserted into the queue as long as its activation count is higher than the minimum activation count in this queue. What this means is that, let's say a queue is full and one of the rows crosses the activation count for far beyond the back-off threshold, and it raises an alert. And in this period, if the attacker tries to pull off a fill and escape attack, we ensure that, let's say the row T receives more activations than the rows that are in the queue. Row T now has the opportunity to be inserted into the queue. So at no point are we losing information about heavily activated rows. And now if the attacker tries to hammer row T and surpass the Rowhammer threshold with row T now moves to the top of the priority queue. And therefore, whenever the mitigation comes in, row T is the one that's going to be mitigated, not the FIFO behavior. Hereby allowing rows that require mitigation, have a higher priority of receiving mitigation, to actually receive the mitigation, we are able to prevent an instance like fill and escape attack. Okay, so with this, QPRAC tracks rows, the activations for rows, even during this intermediate phase where the attacker is using ABO acts to avoid attacks like fill and escape. So with QPRAC, we try to bound the security guarantees by modeling the worst case attacks, basically fainting attacks or the wave attacks that some of you came up with. And we try to model these bounds across a wide variety of backoff thresholds. And we observe that for a backoff threshold of 32, the minimum TRH that this defense can support is somewhere between 50 and 70, which is actually a fairly tight bound, given that Rowhammer thresholds are currently in few thousands. We also model the performance of this defense. We assume a baseline which has the timing parameters of PRAC already implemented. And compared to this baseline, if we simply assume a design like QPRAC, it actually ends up causing a lot of slowdown. So what we observe is that there are a lot of additional opportunities for performing mitigations and not just on alerts. In fact, we observe that when an alert is issued for a particular bank that requires a mitigation, all other banks can also opportunistically mitigate the highest priority rows. With that, with opportunistic mitigation, we're able to reduce the overhead from 12% to something like 0.8%. And further, we can perform mitigations also on TRFEs proactively. And with this, we observe that the slowdown becomes almost negligible. And finally, if we are able to filter out instances where we really need to perform a mitigation by additionally adding one additional condition for when a mitigation should be performed, we are able to filter out cases where a mitigation was really not necessary and thus reduce some of the energy costs also of performing the mitigation. So overall, we are able to produce a mitigation that has low overhead and also low energy. So to conclude, PRAC is a great specification, but really the implementation dictates the security and performance. And prior designs may be insecure or not fully practical based on the design. And QPRAC proposes one of the first practical and secure implementations of PRAC that is secure under fairly low Rowhammer thresholds. Any questions? Yes? Yes. Please.
So PRAC also has the overhead of increasing timing parameters,
Yes.
right? How do you address that in this work? Because you mentioned close to 0% overhead. I was wondering if you got rid of those latency overhead somehow.
Yeah. So that's a good question. So if you notice, the baseline that we assume here actually has the timing parameters of PRAC implemented already. So the assumption here is that CPU vendors or memory vendors have eaten the cost of the increased timings, and our comparisons are with this baseline. So here we are capturing really the performance overheads of actually doing the alerts and not really that increased timings. There are other works like Cronus, for instance, that avoid some of the timing parameters and the overheads of the timing parameters. And I think that's probably the way to go for avoiding the those sets of overheads. But our design decisions are actually orthogonal to some of the Cronus's design decisions. So one could really kind of compose the two together to reduce the overall overheads.
Oh, yeah, I got it. So the baseline is basically a system that already uses PRAC.
Yes.
I have one more.
Sure.
It's not really a question, it's a comment. I feel like I have to correct the record maybe again in slide 34, where you were describing understanding PRAC. It looks like we imply that you need to read all of these and take the overhead of 10 milliseconds before, like every time you need to do, like send an alert 10 signal. I don't believe that's implied in this paper. The best interpretation, I think, would be like, this is left unclear, right? This is how you described it at the start of the slide. Versus how it ended, it looked like we read all the counters to take the 10 millisecond overhead every time there needs to be an alert 10 signal, which I think is a bit misleading when you take it out of context.
So to be really honest, didn't the paper I'm referring to here is the DRAM sec version of the paper, and the way, at least our interpretation of the paper, was that the highest activated row is mitigated, right? It's unclear how that's identified, right? Like there could be different ways of identifying it.
Yeah, I agree.
And this is the most naive way of identifying it. But of course, there could be other ways, right? So yeah, that's the point I wanted to make.
Thanks.
So maybe I can follow up on that. Just for sake of some brainstorming here, I guess it's useful for everyone. So another like naive implementation, I agree that it's not clear in the paper, but because it was not the focus of the paper. But another naive implementation would be like you reduce the backoff threshold to some extent so that you can ensure that when a row activation happens, let's say row C moves from 21 to 22, then you put that row C's information somewhere. So it's the last activated row that triggers the backoff, and then the backoff comes and the memory controller issues the RFM. And since that is the row that triggered the backoff signal, you would go refresh the victims of that row. So in that case, you would not need to necessarily like search and find the maximum activation count, because you like from the beginning, you already know it. You just like remember it by putting it into some register or something like that. So in that kind of implementation, would you find like some other weakness for security? Like why is it not enough?
I think that might work. In fact, that's kind of similar to QPRAC, right? We basically maintain like a local structure that keeps track of n highest activated rows at any given time, and that way you can approximate the highest activated row globally, right? In fact, if you'll notice, even with QPRAC, there are instances where the highest activated row globally in the memory is not the highest activated row locally in the queue. So it's really an approximation of the highest activated row in the system. So I would really have to look at the exact implementation to figure out why it's secure or why it might not be secure. But I think in security, you really need to specify the implementation, right? Only then you can argue whether it is secure or not. So I mean, again, even with QPRAC, we think it is secure, but there could be corner cases where something might break, right? So the best way forward is to actually implement the actual implementation so that we can fuzz it and we can see if it actually works or not in all of the corner cases.
Yeah, did you put this on AMuLeT and try to find?
Not yet, but that's actually a great area for future work to actually start fuzzing some of these implementations and seeing if there exist other corner cases where they might break.
I see. So I'd like to.
I fuzzed that implementation. I think the problem there would be if you have a single register, you don't want to have any ABO acts. The ABO acts are the main problem, right? Because if you consider row C, let's say in this picture, to be the most frequently activated row, and you record it somewhere, and then you send the alert 10, and then another row D might get activated up to 24, and then you repeat this process to the point where they all reach the real Rowhammer threshold, and you end up not refreshing them.
So I guess the assumption is like in that TABO act, you have only like 3 activations that you can fit. So you will have like, I don't know, 4 registers.
Yeah, I think the
Similar
number,
to QPRAC.
Yeah.
the number of table entries relate to the number of ABO acts you can perform.
Yeah, thanks. I guess we are just brainstorming at this point.
But
So,
yeah, it's good that you bring up this question because often the devil is in the details. So this is the most secure way of, okay, this is one way of ensuring that the design is secure, which I think was the intent of PRAC or UPRAC to, figure out what are the bounds and so on. I'm not sure if some implementation that approximates the highest activated row is secure or not, right? This we know is secure. So that's the reason we kind of assume this implementation.
okay, yeah, that sounds good.
Yes.
So are there other questions about your PRAC? Here or on Zoom? No? May I ask more time for like another question? So I guess Atabak's point is like on point actually. So it's this TABO act where like after sending the backoff until receiving the RFM, we have that 180 nanoseconds. As you said, the devil is in the detail. So that sounds a problematic implementation of or restriction in the specifications. So we also had this like earlier paper called self-managing DRAM where we had some similar.
What was the paper?
Self-managing DRAM. I'm not sure if you're familiar.
I think I've heard it or seen it. Yeah.
So over there, what we propose, it was basically a proposal way before the PRAC came out. Basically, what we propose is something like a backoff signal. We call it alert signal. When the memory controller issues an activation, you basically send an alert if you do not want to perform that activation from DRAM side. So basically, you lock some regions for maintenance operations. One maintenance operation is Rowhammer defense. And then you do not perform activations in that region until you're done with your maintenance. So you can consider the like PRAC implementation of like self-managing DRAM is like broader in the focus. But if we look at the Rowhammer specific case, it's identical to PRAC without TABO act. So you have everything that PRAC gives, but you don't have that 180 nanosecond restriction.
Yeah.
So I guess it might have some other like concerns that may rise, but I wanted to pick your brain on like what would you think of like having that kind of specification instead of PRAC, like a hypothetical scenario. You know, the PRAC came out, but there was no 180 nanosecond. Would that be better or would that be worse? Like, would you have more concerns about that?
Yeah. So in a nutshell, your question is, would a PRAC specification without the ABO Act gap be a better specification, right? I think it would definitely be better for security. I think it makes reasoning about the bounds much simpler, and simple is often better for security. I don't know why that was not the design that the JEDEC folks went with. maybe there are practical limitations with that kind of a specification. Your guess is as good as mine. But yeah, maybe this discussion forces the specification folks to consider, maybe reducing that time or eliminating that time altogether. But maybe it exists because of some practical limitations that memory controller designers have. Maybe they want to service some pending activations. You can think about, maybe there is a really critical memory access that needs to go through even when an alert is raised. Maybe that's the reason why this exists. I don't know. I can hypothesize, but I don't know why this gap exists. But
Yeah,
if there are no practical considerations that require this gap, then this should probably go away. And I think Cronus kind of does that, right? Like it proposes to just ensure, at least it has one variant where it says, just do the mitigation immediately after an alert.
Yeah, something similar, but not exactly, I guess. Yeah. No questions? Yeah, maybe we can move on that.
Okay, so I don't have a ton of time, so I'll probably go through some of the Okay, so I'll probably talk about one last word before we part for the day. So to emphasize how offensive thinking can actually improve defenses or our understanding of defenses, I'd like to talk about some of our upcoming work at ISCA, which is what new kinds of attacks can happen when an existing new mitigation comes in. This is work led by a student at UBC and also done in collaboration with folks at UBC. So the key observation here is that the alert that is raised on a, so when an alert is raised, the RFMs that are part of the backup protocol actually freeze an entire rank, right? They're all bank RFMs. And this all bank mitigation actually is visible across the system, right? So if you have a victim and an attacker running on two cores of a system, and they share a part of the DRAM rank, an ABO introduced by a victim activity can be observed by an attacker. So in this case, I show you two graphs. In the first graph, you have, in both graphs, you have an attacker performing memory accesses and measuring the latency of its memory accesses. In the top graph, we have no victim activity and no ABOs introduced by the victim. In the second graph, you have victim activity that actually causes ABOs. You'll notice that in the second graph, the attacker's memory accesses start to have spikes, latency spikes. And these latency spikes in red are actually correlated with ABO instances due to victim activity. So in short, PRAC ABOs allow an attacker to observe or spy on victim activity that causes ABOs. To make matters worse, these ABOs are actually dependent on not just victim activity, but they're dependent on how many activations are performed by the victim. So one can actually use these ABOs to not just learn that victim is accessing the memory a lot, you can learn exactly how many activations a victim has performed on a given row. Let's consider a situation where a row is shared between an attacker and a victim. In the bottom graph, you will see, on the left side, the victim activations are happening at different rates to different rows of the DRAM. And on the right, you will see after the victim finishes execution, the attacker starts activating all of these rows uniformly. by simply observing when an ABO is observed, the attacker can figure out, let's say, how many activations the attacker performed to cause the ABO. And by subtracting this number from the back of threshold, the attacker can also figure out how many activations were performed on that row by the victim. So this is actually a very powerful side channel that not only leaks victim activity, it allows an attacker to observe exactly how many activations a victim has performed on a given row. This is actually bad because we can now use this information to perform side channel attacks. So we take as an example an AEST table attack, which is an attack, a chosen plaintext attack on the first round of the AES, using an old implementation that is known to be vulnerable to side channel leakage. In this case, what happens is that the attacker is able to cause one of the cache lines of the AEST table to have more number of accesses compared to the remaining cache lines. And if these cache lines are uniformly distributed across, let's say, 16 rows, we will start to have one of the rows having higher number of activations compared to the other rows. And if the attacker can figure out which is the row that has the higher activations, they can figure out some bytes of the secret key. So with this ABO-based side channel, we can show that the attacker, in this case, can observe which row has the highest activation counts across the other rows, and then figure out what is the secret key byte. So in the x-axis, we show that the value of the secret byte as it varies, and the y-axis shows which is the shows the different rows, and the heat map shows the intensity of activations. And you'll notice that there is a strong correlation between the row that has the highest activation count on the right side and the value of the secret byte. So by using these ABOs, the attacker can actually learn which row has the highest activation count and thus leak some bytes of the secret key in AES. Using this primitive, we can also launch covert channel attacks, where the attacker and the victim share a DRAM row. And there are two types of attacks that are possible. One is the activation count-based, where the victim communicates information to the attacker based on its activation count in any given time window. Or this, so here, the attacker can send n bits, which is the value of the activation count itself as part of its payload, or simply activity-based, where in any given window, the victim, or rather the Trojan, basically has a lot of activity that causes an ABO to signify bit 1, or it doesn't have any activity to signify bit 0. And in both of these covert channels, we observe that the attacker can transmit information at the bit rate of anywhere between 10 to 100 kilobits per second. And the activation count-based attacks are able to transmit higher bit rates simply because they transmit in one window n bits compared to the activity-based attack, which simply transmits 1 bit per window. So with this, we are able to transmit information at fairly high rates that can be weaponized potentially in attacks like Spectre. Finally, we also came up with defenses. In this case, we came up with a fairly simple and straightforward defense. The idea is to replace mitigations with ABO that are inherently activity-based and make it more timing independent, where the memory controller sends mitigations at a rate that is independent of the victim activity. These mitigations can be sent at a fixed rate, or they can also be sent at a variable rate based on how much you want to hide this information leakage. By co-designing these mitigations with also opportunities for performing these mitigations on TRFEs, we're able to reduce the slowdown of this mitigation to close to 1% of baseline PRAC at TRH of few thousand. If we go to lower TRH, of course, the overheads of this kind of mitigation kind of blow up. So future works can definitely look at ways to perform these mitigations with lower overheads. So I'll conclude with I'll conclude this talk with 3 key messages. First, security is crucial for next generation systems and hardware. It's important to think of security for designs, not as post facto after commercialization, but really to start thinking about these, security of these defenses and insecurity potentially of these defenses at design time, because if we commercialize it, then it becomes hard to patch. And applying this offensive mindset at design time can actually help us come up with more robust defenses that are likely to stand the test of time. So I hope all of us in this room can take this message and start thinking about ways in which the defenses we design can break so that we can come up with better defenses in future. Thanks, and happy to take any questions.
All right, I guess I'm gonna ask for questions for the last part first, and then people can ask for any part, I guess. I assume we don't have any strict time restrictions.
Also handing the other microphone to any takers. Okay, I guess we had the chance to talk about this work, but I have some more questions.
Sure.
Nice talk, thanks for presenting. We previously talked about synchronizing the sender and receiver in the covered channels and the numbers over there. I want to ask some more clarifications on that. Since you're leaking the activation counter value, you can send multiple bits at once, but this comes with a price, I guess, about synchronizing the sender such that it executes before the receiver side. And I was wondering if you have evaluated some methods for synchronization, or the results, do they have that overhead?
So the numbers that you'll see are actually upper bounds. If you'll notice, we don't have any errors. So definitely, once we start trying to synchronize the sender and receiver, that's going to cause a lot of errors. And trying to push up the the number of bits you send with each ABO is going to mean that they might be more susceptible to errors, right? So this is more like channel capacity, if you want to consider that as the metric that we evaluated here. I think once you start to have errors due to issues practical issues like synchronization and so on, one would want more sophisticated error correction mechanisms or other layers built on top of this to make sure that you can reliably still transmit at a high bit rate. This might come at some additional cost in terms of reducing your bit rate a little bit, but I think most code channels are likely to suffer from noise and so on in practical settings. So techniques that are used in other covert channels are as applicable here.
Yeah, okay. I guess when we consider main memory based ones, for example, drama, the synchronization methods over there are very simplistic, right? You execute the sender and receiver at around the same time. And since they're building the same state changes, they sort of don't need that serialization of the sender and receiver. So we are also experimenting with, we have this work about the same vulnerability, right? And we also tried some similar attack vectors, and basically the synchronization made it very hard to send at high rates, such that we didn't see any benefits from sending multiple bits. But yeah.
So I think it really depends on this kind of setting that you're trying to synchronize the Trojan and the spy. So for instance, if you have a privileged, think about confidential computing kind of setting where your hypervisor is the malicious entity, often over there, it's easier to perform synchronization as the hypervisor can, preempt a particular victim that is running inside a VM from running, perform certain initial operations to prime, run the VM for a certain amount of time, and then preempt the VM again and try to infer what happened, right? So in those cases, the synchronization can be very, very easily engineered, and that's less likely to kind of be susceptible to noise that you're talking about. In other settings where you're trying to do this, cross-core, I would expect these kind of problems to crop up much more. So it really depends on the setting that you're, studying the covert channel in, and your, the bit rates can vary very, very widely based on
Yeah. So I guess I agree. In the case of like side channels that you presented, we also talked about the bit rate. And over there, it's much easier to synchronize when you assume a certain scenario. But with covered channels, like you mentioned, it's a bit more difficult. I have another question if no one has any burning questions right now. So it's about, again, the noise and the attack success rate. I guess you did not experiment with other applications being in the same system. So I was wondering, since we have this like DRAM mappings that do this like bank interleaving and so on, one row can be shared by many applications. And I was wondering what would be the impact of that for your side channel, for example. Do you think that would have an impact, or do you have any results on that?
So basically, if you have one row shared by many applications, you would really, for noise to start appearing in these observations, you would need a specific row that an attacker is observing, that the victim is also accessing. That same row needs to be not just be shared with other applications, it also needs to be activated by that application in that period, right? So the chance of that happening in general is low, but it definitely can occur. At that point, the one way that popularly people use is to have many observations. So if you repeat the observations of the same bit being transmitted, it's likely to normalize the noise, basically average out the noise and preserve the signal. And that's one way to kind of retain the signal being transmitted despite multiple applications running. So it basically means that you need to try more attempts, but that doesn't change the inherent leakage.
So the success rate would be maintained, I guess, but maybe the performance or like the speed of the attack would be impacted.
Exactly.
Okay. Thanks for the answers. Does anyone have more questions, I guess?
So I got distracted and partially missed the mitigations. So I'm not sure if you mentioned it, but I'd like to ask one question. So if you have an attack that exploits the latency difference and you trigger it by using some user level application, then like in principle, if you somehow stop this application from working or accessing memory, then you already get rid of the problem, right? As part of, as a mitigation mechanism. So you can easily detect which process is causing this kind of behavior, and you can ban them from accessing memory so that you don't have a covert channel, you don't have a side channel, you don't have anything. So did you explore this avenue or do you have plans on exploring on this?
I think that's a good way to kind of mitigate some of these problems. Attack detection is always a promising direction for, performing mitigation, like addressing some of these problems in the cloud, because you have the option of, relocating potentially malicious VMs to some other system that is not going to be shared by the attacker and the victim. So all of those kinds of attack detection and approaches to relocate the potentially malicious VMs are totally applicable to even this particular attack, timing attack. In fact, it's even applicable to Rowhammer attack because at the end of the day, you're really looking for patterns that are hammering memory. And if you see one particular program that is hammering memory a lot, you can always kind of relocate that particular VM. So all of those directions are definitely possible. We did not explore it in this paper, but yeah, that's a valid approach.
Okay. Yeah, if you want to build on that, I want to promote our paper Breakhammer,
Sure.
where we detect which thread is doing Rowhammer and throttle the process based on that. I guess, yeah, there can be some synergy. I guess in your paper as well, we discovered it a little bit, right? We explore it. Yeah. So.
I don't know if you have seen it, but maybe I can ask it. So it's about the mitigation that you mentioned. How do you determine the periods for the RFM?
How do you determine what?
The period of, like, the frequency of RFMs to decouple it from the preventive actions.
So how do we determine the frequency? So basically what we do is we, for a given Rowhammer threshold or given backoff threshold, for a given Rowhammer threshold, we try to find what is the minimum period at which a particular mitigation needs to be sent, right? And with this timing independent approach, the idea is that it should be sent at the maximum, or rather the minimum rate that is required for the defense to be secure at a given Rowhammer threshold. So what this means is that for 1,000, it might be a particular rate. For 100, it might be 10x the rate, and so on. That's the reason why the overheads kind of grow as the Rowhammer threshold drops. One optimization we did is that if you have proactive opportunities for doing the mitigation on TRFEs, we include those opportunities within the calculation for how many mitigations need to be sent to the DRAM for mitigating Rowhammer. So what that means is that basically means the frequency of extra mitigations being sent to the DRAM can be slightly lower than the theoretical number we calculate, which allows us to kind of keep the overheads lower, slightly, at Rowhammer thresholds of 1,000.
Okay, I have a follow-up question.
Sure.
I'm asking a lot of questions, sorry. So again, we were like exploring the similar mitigations, and since we were also basing it to RFM and this like periodic RFM in the terms of like the activation counts, not in terms of time, and the thresholds, that the period was sort of like similar to what could take us to activate like the threshold times, drops or something like that. Anyways, I was wondering, like, because we see that RFM-based solutions tend to break at very low Rowhammer thresholds, like below than 128. Do you also observe a similar change in the trends? Or
Yeah. I mean, if you try to scale this to something like 100, it would cause crazy overheads, and this would really not work at a TRH of 100, right? So that's really something that we need to focus on for future work, because coming up with defenses that don't have this leakage, which are also practical at low overheads, low Rowhammer threshold, is kind of like the holy grail right now.
I guess that makes sense, because at really low Rowhammer thresholds, this is still an open problem, I guess.
Yeah. Okay. Maybe some kind of randomization or probabilistic methods might work at that scale, because over there, the goal is not to completely eliminate the signal, but to make it imperceptible from maybe random guess.
Yes, that's actually a good way for me to plug my paper. That's something that we explored, I guess. Yes. Okay. Thank you.
So if people on Zoom have questions, they can speak up as well. Okay, then I'll just say that on Friday, we will have Biswaban and Panda on high performance and secure processor designs. So please stay tuned with Safari Live seminars. And let's thank our speaker today, Gururaj.
Thank you.
Thanks a lot for coming here.
Thanks for organizing and thanks for attending.
Okay, yeah, we can end the live stream now. Content to cover in like 1 hour.
My laptop. So.